In my third lecture, I will actually be talking about rumor spreading on random graphs and very simple models for that, which sometimes go under the name of first passage percolation. So pick your favorite random graph model, GN, so it could be GMP, Erdős and Rényi random graph, or the configuration model, or whichever graph you particularly like. And of course this I will always think about as consisting of n vertices to start out with, and then there is a collection of edges in the graph. And now what we do is to all of the edges we associate a random traversal time. So I have an E in my edge set, and it's corresponding a YE, which I think of as a traversal time. Now, an example would be an exponential random variable or something like that. And then what we would like to do is shortest path routing. So we start from a source vertex, let's say V1, and we want to see how quickly we're going to be spreading our rumor around. So what does it mean to spread the rumor? Well, at some time t, I will have seen all the vertices, let's say in a ball of width t around my initial vertex, V1, which is all the vertices for which the traversal time between my starting point and V is less than or equal to t. So if you think about a rumor spreading, it actually takes a random amount of time, YE, to spread the rumor across edge E, if it starts out from V, and then this is the set of all the people who have actually heard the rumor at time t. Okay? So this has been studied quite frequently when we study, for example, a random starting point and a random ending point. So this would be the amount of time that it takes the rumors to spread to a typical individual. But you could also ask for many different questions. And the different questions could be, if I have my starting point, how long will it take, suppose that my graph is connected, how long will it take the rumor to spread to the entire graph? So that's sometimes called the flooding time. So that's the infimum over little t, such that bt of my starting point is actually the whole graph. Okay? How does this behave? As the graph tends to infinity, it will probably take longer for all the vertices to be found. Okay? And in particular, how does it depend on the precise distribution of this traversal time? That's not known. This problem has not been understood or not been investigated for general edge distributions. There's one case that has been understood, and that is when YE is exponential, say with parameter 1. Because of course in this problem multiplying things by a constant doesn't matter. And I believe that this is actually a particularly interesting case, which is on the boundary between two different phases. Why? Well, for this flooding time, what is important to notice is that there might be vertices for which it takes a very long time to reach in. That's somehow a local trap. So it takes a very long time for the information to go there, even though all its neighbors already know the rumor. So what does that mean? So traps are of the kind, you have a V, you have edges coming out of it. So all YE for E that contain V are large. So Svante Jansson has a paper about this on the complete graph. This is in 1999. With a nice title, 1, 2, and 3 times log n over n for weighted complete graphs. This is on the complete graph. And he denotes these as being Oberwolfach. Who's been in Oberwolfach? Some people. Oberwolfach is not easy to get to. It's a very small village. You have a long time to get there. So these are the Oberwolfachs of our society. Now, what is special about exponential is that these local traps are typically of the same order of magnitudes as typical paths. Okay? And that's what makes this a particularly nice case. So somehow, YE exponential, somehow the depth of the deepest trap has the same order of magnitude as the typical rumor spreading time. And therefore, these compete with one another. Okay? The case where the YEs either have thinner tails or thicker tails, they're more heavy-tailed or they're less heavy-tailed than exponential, is quite different. So if they're thicker, then the depth of the deepest trap can actually be much larger than the typical rumor spreading time, which in many of these cases is of the order log n. So there can be traps that are way, way, way deeper than log n. And then somehow it seems to suggest that you get this flooding time by looking at the worst possible trap and just go there. That's probably true in first order asymptotics. But is that also true in second order asymptotics? That's not known. So this would be thicker tails. Conjecture. The flooding is deepest trap. So the time to get out of the deepest trap times 1 plus small op of 1. Right? And you can go one level further and ask, well, what is this smallest fluctuation? So that's for thicker tails. If you have thinner tails, then somehow the traps are much smaller. So the deepest trap actually is not of the same order of magnitude as log n. So what happens then? Is this related to large deviations? Of, let's say, continuous time branching processes that describe? First passage percolation, which is the same, a different word for this rumor spreading model on random graphs? I don't know. So what I would be interested in is higher order asymptotic statements as to how this flooding behaves. So here, for example, it could very well be that depending on the precise thickness of the tail, that you get the deepest trap, plus an order of magnitude that is very similar to, let's say, the typical traversal time. Because there's going to be one best neighbor of your trap, which you're going to be finding first, and then you just have to go there. That's the best thing you can do. Right? So that suggests a possible way of getting there. Not clear that this is the best possible strategy. I think there are lots of interesting problems here, and we basically don't know anything yet. So the only exception, as I said, is a paper by Amini and Lelarge, I think sometime around 2013 or so, where they do first order asymptotics. On the configuration model, for which you now all know what it is, for exponential. And as I said, in the exponential case, the order of magnitude of the deepest trap is of the order log n. It's not very difficult to see this. And that actually competes with the typical distances in this graph. And they actually prove that if you look at this first order asymptotics, then it's a constant which is slightly larger than for it's a constant times log n, where the constant is slightly larger than the constant for typical vertices. Any questions? You may ask many more problems. I mean, what is the longest path in terms of the number of edges? So Yuval has an interesting paper about that on the random regular graph, and also exponential edge weights. But for more general configuration models, as I've understood, this problem is still open, right? Yuval? Yeah. So I'll be addressing such problems, but not for flooding, in my very last lecture on Friday.
Thank you.